To comprehend the sheer magnitude of destructive capability and technological sophistication embodied within the United States Navy's most powerful destroyers, one must fundamentally recalibrate their understanding of naval warfare, moving away from historical paradigms of broadside gun duels and entering a realm dominated by the electromagnetic spectrum, hypersonic ballistics, and advanced directed energy potential. The title of Most Powerful Destroyer in the American Arsenal is a complex duality, split between the futuristic, stealth-oriented Zumwalt class, DDG-1000, and the heavily armed, sensor-dominant Arleigh Burke-class Flight III, exemplified by the USS Jack H. Lucas, DDG-125. Both vessels represent the absolute zenith of maritime engineering, yet they achieve their lethality through entirely different operational philosophies and structural architectures. The journey into the heart of these leviathans begins with the USS Zumwalt, a ship that looks less like a traditional man of war and more like an obsidian dagger slicing through the ocean's surface. The defining physical characteristic of the Zumwalt is its wave-piercing tumble-home hull. Unlike conventional ships, whose hulls flare outward above the waterline to increase buoyancy and deck space, the Zumwalt's hull slopes aggressively inward. This design, pioneered through extensive computational fluid dynamics and scale model testing, serves a dual purpose. It allows the vessel to cut cleanly through waves rather than riding over them, significantly reducing acoustic signature and wake, and, most crucially, it deflects enemy radar waves upwards into the atmosphere or down into the water, rather than back to the receiving sensor. This architectural choice, combined with a composite material deckhouse that encloses all antennas and sensor arrays, grants a warship displacing nearly 16,000 tons the radar cross-section of a small fishing boat. This level of stealth is not merely a defensive attribute, it is a profound offensive enabler, allowing the destroyer to operate deep within contested littoral waters, effectively bypassing adversary anti-access and area denial networks before unleashing its payload. Beneath the carbon fiber and radar-absorbent materials of the Zumwalt lies its true engineering marvel, the integrated power system. Traditional warships utilize a bifurcated mechanical layout, where massive gas turbine engines are physically coupled to the propeller shafts via immense reduction gears to drive the ship, while separate, smaller generators provide electrical power for the ship's sensors, weapons, and hotel services. The Zumwalt completely shatters this paradigm. It is equipped with two massive Rolls-Royce MT-30 marine gas turbines, derivatives of the Trent 800 engines that power the Boeing 777 airliner, and two smaller Rolls-Royce RR4500 turbine generators. However, these turbines do not mechanically drive the propellers. Instead, they operate strictly as massive electrical generators, feeding into a colossal ship-wide power grid capable of producing a staggering 78 megawatts of electricity. This is enough power to illuminate a small to medium-sized city. This electricity is then distributed dynamically across the ship to wherever it is needed. Massive advanced induction motors utilize this electrical power to drive the propeller shafts, propelling the massive ship at speeds exceeding 30 knots. The strategic genius of the integrated power system lies in its flexibility. Because the propulsion system is entirely electrical, power can be instantaneously diverted from the drive motors to power next-generation weaponry and sensors. As the United States Navy moves aggressively toward the fielding of high-energy solid-state lasers for point defense against drones and anti-ship cruise missiles, as well as high-power microwave weapons to scramble enemy electronics, the Zumwalt is structurally and electrically pre-configured to accommodate these power-hungry systems without requiring the massive, highly invasive redesigns that older classes of ships would demand. The offensive teeth of the Zumwalt are equally revolutionary, though their history is fraught with complex procurement challenges. Originally designed as a premier land attack platform to support amphibious operations following the retirement of the Iowa-class battleships, the primary armament of the ship was intended to be the advanced gun system, consisting of two massive 155mm automated naval guns firing the long-range land attack projectile. These GPS-guided, rocket-assisted projectiles were designed to strike targets nearly 100 miles inland with pinpoint precision. However, as the production run of the Zumwalt class was drastically reduced from 32 planned vessels to a mere 3, the USS Zumwalt, the USS Michael Monsor, and the USS Lyndon B. Johnson, the economy of scale collapsed. The cost of a single long-range land attack projectile skyrocketed to nearly $1 million, making the system financially unviable. The Navy was forced to make a ruthless, pragmatic decision, leaving the guns aboard but inactive, completely pivoting the ship's strategic purpose from literal land attack to blue water surface strike and hypersonic missile delivery. To achieve this, the Navy is currently in the process of physically removing the advanced gun systems from the Zumwalt to make way for the integration of the Common Hypersonic Glide Body, part of the conventional prompt strike program. These hypersonic missiles, capable of traveling at speeds exceeding Mach 5 and executing complex atmospheric maneuvers to evade ballistic missile defenses, require massive launch tubes that cannot fit into standard naval vertical launch systems. The Zumwalt's immense size and internal volume make it the only active surface combatant capable of accommodating these strategic weapons, transforming the ship into an unparalleled long-range strike asset capable of holding high-value enemy targets at risk from thousands of miles away. Complementing this future hypersonic capability is the Zumwalt's unique Mk-57 peripheral vertical launch system. Unlike traditional destroyers and cruisers, which cluster their missile silos in massive blocks along the ship's centerline, the Zumwalt distributes its 80 missile cells around the outer perimeter of the hull. This design is a masterclass in modern damage control and survivability. If a conventional destroyer takes a direct hit to its central missile magazine, the resulting sympathetic detonation of its own weapons will almost certainly obliterate the vessel, snapping the keel and sending it to the bottom. On the Zumwalt, the peripheral cells are designed to direct the explosive force of an internal detonation outward, away from the ship's vital interior spaces and crew compartments. These Mk-57 cells are larger and heavier than the standard Mk-41 systems used across the rest of the fleet, allowing them to carry larger, heavier future missiles, alongside the current arsenal of SM-2 and SM-6 standard missiles for air defense, evolved Sea Sparrow missiles for point defense, and Tomahawk cruise missiles for deep strike. The sensor suite orchestrating this firepower is the dual-band radar system, utilizing the AN/SPY-3 X-band active electronically scanned array radar. This system provides unprecedented resolution and tracking capability, specifically optimized for detecting low-altitude, low-radar cross-section threats like sea-skimming anti-ship cruise missiles in highly cluttered littoral environments, seamlessly integrating with the ship's combat management system to provide automated, instantaneous threat evaluation and weapon assignment. While the Zumwalt represents the ultimate expression of specialized, stealth-oriented strike warfare, the title of the Navy's most powerful workhorse, the undisputed master of wide-area air and missile defense, belongs to the Arleigh Burke-class Flight III destroyer. If the Zumwalt is a sniper rifle, the Flight III Burke is an impregnable, heavily armed fortress. The Arleigh Burke design has been the backbone of the United States surface fleet since the early 1990s, but the Flight III variant, beginning with the USS Jack H. Lucas, represents a generational leap in combat capability, driven almost entirely by the necessity to counter the rapidly expanding, highly sophisticated missile arsenals of near-peer adversaries in the Indo-Pacific theater. The absolute core of the Flight III's power, the very reason for its existence, is the AN/SPY-6 V1 air and missile defense radar. The previous generations of Aegis destroyers relied on the venerable AN/SPY-1 radar, a passive electronically scanned array system utilizing gallium arsenide technology. While formidable in its time, the SPY-1 is reaching the limits of its physical capability against modern threats. The SPY-6 is an active electronically scanned array built using gallium nitride technology. Gallium nitride is a highly efficient semiconductor material that allows radar transmit-receive modules to operate at significantly higher voltages and temperatures than legacy materials. This translates into a radar that is exponentially more powerful, more sensitive, and far more resilient to electronic jamming. The SPY-6 radar on the Flight III destroyer provides a staggering 30 times increase in radar sensitivity compared to the older SPY-1. In practical tactical terms, this means the ship can detect incoming ballistic missiles, supersonic cruise missiles, and stealthy fifth-generation fighter aircraft at vastly greater ranges, tracking twice as many targets simultaneously while guiding multiple interceptor missiles to their targets with absolute precision. The radar is highly modular, constructed from standard, self-contained building blocks called radar modular assemblies. The Flight 3 destroyer carries 37 of these assemblies in each of its 4 massive radar faces, providing seamless 360-degree coverage from the stratosphere down to the wave tops. This radar is the primary sensor for the Aegis Baseline 10 combat system, a highly sophisticated, deeply integrated software architecture that fuses data from the Spy-6, the ship's sonar arrays, electronic warfare suites, and off-board sensors via data links to create an unparalleled picture of the battlespace. When a threat is detected, the Aegis system can autonomously calculate firing solutions and launch the appropriate interceptor from the ship's 96 Mk-41 vertical launch cells. The Flight 3 is armed with a terrifying array of defensive weaponry, including the SM-3 Block IIA missile, designed to intercept intercontinental ballistic missiles in space, the SM-6, a versatile hypervelocity missile capable of shooting down aircraft, cruise missiles, terminal phase ballistic missiles, and even functioning as an anti-ship weapon, and the ESSM Block 2 for short-range kinetic intercepts. Accommodating the immense power and cooling requirements of the Spy-6 radar required profound engineering modifications to the proven Arleigh-Burke hull. The radar generates vast amounts of heat and requires immense electrical power to function at peak capacity. To facilitate this, naval engineers heavily modified the Flight 3's electrical plant, replacing the older 3-megawatt generators with 3 massive 4-megawatt Rolls-Royce generators. They completely redesigned the ship's power distribution network, transitioning from a 400-volt system to a highly efficient 4,160-volt system, mirroring the high-voltage architecture found on nuclear aircraft carriers. Furthermore, the ship's cooling capacity was massively expanded. The air conditioning plants were vastly upgraded, and the chilled water distribution system was entirely re-engineered to pump thousands of gallons of coolant through the radar arrays to prevent the gallium nitride modules from melting down under the extreme thermal loads generated during combat operations. The hull itself had to be structurally reinforced and slightly widened at the stern to maintain stability and buoyancy with the added top weight of the massive new radar arrays and the heavier electrical and cooling infrastructure. The result is a ship that, while visually similar to its older sister ships, is an entirely different beast internally, specifically built to dominate the electromagnetic spectrum and provide an impenetrable umbrella of air defense over carrier strike groups and vital maritime choke points. The strategic employment of these vessels illustrates their respective roles within the broader American naval doctrine. A Zumwalt-class destroyer, operating independently or as part of a specialized surface action group, would leverage its stealth to penetrate heavily defended maritime perimeters. Operating in a condition of strict emission control, the ship would rely on passive sensors and off-board targeting data to silently approach its launch point. Once in position, the Zumwalt would unleash a devastating volley of hypersonic glide bodies, instantly decapitating enemy command and control nodes, destroying integrated air defense networks, and neutralizing long-range anti-ship missile batteries hundreds of miles inland, effectively kicking down the door for follow-on conventional forces. Its acoustic quietness also makes it a formidable anti-submarine warfare platform, capable of stalking adversary nuclear attack submarines with its advanced dual-frequency hull-mounted sonar and towed arrays. Conversely, the Flight 3 Arleigh-Burke is designed to stand in the main battle line. Assigned as the primary air defense commander for an aircraft carrier, the Flight 3 would utilize its SPY-6 radar to project a massive, protective sensor net over hundreds of miles of ocean. In a high-intensity conflict scenario, such as a localized engagement in the South China Sea or a defense of the Taiwan Strait, the Flight 3 would be subjected to complex, multi-axis attacks consisting of swarming drones, sea-skimming cruise missiles, and high-altitude ballistic weapons. The Aegis Baseline 10 system would instantly prioritize these threats, rapidly volley-firing SM-6 and SM-3 missiles to engage targets at their maximum kinetic ranges, relying on the sheer processing power of the Spy-6 to maintain tracks and provide mid-course guidance updates through dense electronic jamming and countermeasure environments. The synthesis of the technologies developed for both the Zumwalt and the Flight 3 Arleigh-Burke is currently laying the foundational architecture for the United States Navy's next-generation guided missile destroyer program, currently designated as DDG-X. The Navy has recognized that while the Arleigh-Burke hull has been one of the most successful naval designs in history, the Flight 3 variant has absolutely maximized the physical space, weight, and power generation limits of that specific hull form. There is simply no more room to add larger radars, larger missile cells, or the massive power banks required for future directed energy weapons. The DDG-X will likely combine the revolutionary integrated power system and stealth characteristics pioneered by the Zumwalt with an expanded, more powerful iteration of the Spy-6 radar and Aegis combat system found on the Flight 3 Burke. It will feature a newly designed hull with significant margins for future technological insertion, allowing the Navy to seamlessly upgrade the ship's weapon and sensor systems over its 50-year lifespan without requiring the massive structural teardowns that plague current modernization efforts. The engineering lessons learned from mitigating the thermal loads of the Spy-6, the complex power routing of the Zumwalt's electrical grid, and the survivability design of the peripheral vertical launch systems will all converge in this future warship, ensuring that the United States maintains its maritime supremacy in an era of rapidly accelerating technological warfare and intensifying great power competition. The destructive capability housed within the steel bulkheads of these destroyers is not merely a display of military hardware. It is a profound manifestation of advanced physics, material science, and strategic engineering, designed to execute the most complex, high-stakes tactical maneuvers on the planet while operating in the most unforgiving, hostile environments imaginable. I can provide a highly granular technical breakdown detailing the precise algorithmic threat evaluation processes within the Aegis Baseline 10 software suite or elaborate on the thermodynamic principles governing the cooling infrastructure of the AN/SPY-6 radar system to further expand your understanding of these specific naval architectures.